calculating scattering amplitudes of your strike theory. Okay, we've got we have the formulas for calculating correlation functions of the operators we will need for the scalar field sector as well as for the C-cross. So let's start. Let's try to compute 3-point functions of stacking fields. Okay. Now later when we actually start calculating 4-point functions and so on, we will use the invariance of, we will use the fact that when we insert operators at given points, it doesn't matter where we insert them. Okay, but for the first few calculations, we'll actually check to see that it's working. Just to get it. Okay, so what are the tachyon vertex operators? It's e to the pi k1 at x1 at sigma, e to the pi k2 dot x2 sigma, sigma 1, sigma 2, and e to the pi, let's call it k3 dot x, dot x is x, x. Remember that these are, so this is the correlator we want to get together with C at sigma 1, C at sigma 2, C at sigma 3. Because we have exactly 3 vertex operators, we have to do no integration, so all 3 operators are fixed. Okay? So we just have to calculate this correlation function, which that's scattering. So let's first calculate this correlation function and then talk about what else we need to add to get the scattering. So first the correlation function. Now, let's first do systematically and then see how we conduct more simply. First, remember that all these operators are on Marsh check. So they obey the equation alpha prime k1 squared by 4 is equal to 1. Okay, they're all dimension 1, 1 operators, and alpha prime k1 squared by 4 was the left and right dimension of the path of x. Okay, so now let's use our general formulas. Our general formulas for the correlating functions of many products of e to the pi k dot x's was product over I and j, product of the pairs I and j, times z I j mod squared to the power alpha prime ki dot kj by 2. Okay, so this is the x part. Okay, so this is just writing it out in this case as z12 mod squared to the power alpha prime k1 dot k2 2 z13 mod squared to the power k1 dot k3 by 2 alpha prime z23 mod squared to the power k2 dot 3 by 2. Now you might think that this is pretty complicated dependency because it depends on all this k1, k2, k3 and how the hell is it cancel. You remember that the answer should be independent of z1, z2 and z3. Okay? However, if you think about it a little more, this answer does not depend on k1, k2, k3. Let's see why. It does not depend on k1, k2, k3 because k1 dot k2 is equal to k1 plus k2, so the thing squared, minus k1 squared minus k2 by 2. But by momentum conservation, k1 plus k2 is just k3 squared. And each of these k's obeys the Marsh definition. So each of these brackets is simply alpha prime by 4. Okay? So k1 by k2 is equal to minus alpha prime, is just 4 by alpha prime. So minus 2 by 3. Okay? So this answer here is actually very simple. It's actually z12 mod squared, z13 mod squared, z23. The power minus 2. Is this clear? Now let's multiply this by the contributions of the C's. the C contribution. The C contribution was simply Z12 mod squared, Z23 mod squared, Z32 mod squared, X part, C part. And so here it cancels. That result is 1. Okay? So the answer to this correlating function more precisely is the answer to the partition function. So let's call that CS2 times 1. What I mean is that there's an undetermined sort of determinant factor outside everything that are called CS2, and every time we compute correlation functions on the sphere, we get a similar factor. So since we're not being very careful about how to value this determinant and define its term, there will be some overall normalization constant which will depend only on the manifold in which we're doing the calculations. Okay, so it's some constant that depends on the fact that we're working on the sphere and then times. Okay. Now we still have to develop our rules for calculating spin scattering amplitudes. Okay, so something that we will provisionally do. You see, we've added, we've used, we've said that in order to compute the scattering amplitudes of given states, you need to put vertex operators of these states on the sphere. But when you do this in Feynman diagrams, you know, with each vertex insertion in a particular normalization, you also put a factor of a coupling constant. Okay? So, what I'm going to do is to leave open the fact that every time we add a vertex operator of a given sort, okay, we should be multiplying this vertex operator with some as yet undetermined normalization. Okay? So, I will leave open the fact that the actual scattering amplitude in string theory is not the correlating function of these vertex operators normalized as I do. After all, who told me to normalize the vertex operators like this? Okay? But the actual vertex operator, let me call it G tachyon, and this normalization could be different in different fields. Okay? That it is e to the power I k of x. We will later use consistency to determine what G tachyon is in terms of something else. Okay? So, with all of this in place, is the real vertex operator. The thing that you need to put into the sphere diagrams in order to compute. Okay? So, being completely general, not committing to any particular normalization, the final scattering amplitude that we've computed is CS2 times G tachyon the whole thing cube times 1. Okay, this is 3 times. Okay, now before going on to do more complicated calculations, let's look at a couple of features of this calculation. You see, the Z1, Z2, Z3 dependencies in the final answer. Can anyone tell me why it was obvious that this had to happen without doing any calculations? Sorry? It should be conformally invariant. But suppose we were just conformal field theorists. And I gave you, okay, let me take more simple. Suppose I gave you the 3-point function of these operators involving only x. Then I'm claiming without knowing very little about the operators, you can immediately predict the Z1, Z2, Z3 dependence of this 3-point function. Can you tell me how? Exactly. Just by scaling. You see, suppose you've got an three operators that transform like H1, actually we do just analytically at the end. So suppose there are H1, H2 and H3. Okay? And I want to compute the correlation function of these three operators. Okay? Then scale invariance determines that they transform like 1 over Z1 to the power H1 plus H2 minus H3 by 2. I'll write it up top. And similarly for the anti-academics. This is just a general result of conformal invariance, depending just on the weights of these operators. Okay? Now, in this case, since we're dealing with string theory, all vertex operators have weight 1. Okay? So, H1 plus H2 plus H3 by 2 is, this is mod squares. Just notes. I mean, the anti-monomer part will be yeah, but we're getting half. Just the analytic values. Just a minute. Let's add up all the weights of this thing. It's H1 plus H2 plus H3 by 2. Yeah, so sorry. So if I write it this way, it would be. Because if we add up all the weights, right. So we just add up, the net weight of each of these. H1 plus H2 plus H3, and we get that at the end. Because okay. Sorry, yes. So these conventional values this way. The basic point is that, suppose we were to complete this, we're writing this in terms of mod z squared. I mean, that's, this is the right answer. Okay, so, now since we're doing string theory, and H1, H2, and H3 are each equal to 1. Okay? This thing is just 1 over Z1, 2 to the power 1, 1 over Z2, 3 to the power 1, 1 over Z4 to the power 1. And that cancels the explicit dependence from the C's. Perhaps the even easier way to say it is that C times V is a primary operator of weight 0. Okay, so the 3-point functions are 3 primary operators of weight 0. Just have Z1 to the power 0, Z2 to the power 0, Z1. So the Z dependence was necessarily automatic. We didn't need to do all this complicated stuff in order to see that it doesn't depend on Z1, Z2, Z1. Okay, all of this work was necessary just to get the number. Okay? Great. Now let's move on. So, now that we've understood what the 3 tachyon scattering vertex calculation is, let's try another one. How about 2 tachyons with a gravity, or a massless closed string state? Okay? So, what's the vertex operator we're interested in? So, we've got some G, so we've got GT then squared times GM with G to the massless states. Okay? Times e to the power k1 dot x times del x mu del bar x nu, and let's put a polarization e mu. Okay? Times e to the power k1 dot x times e to the power k2 dot x times e to the power k3 dot x. And in the first place, everything is at sigma 1. Everything here is at sigma 1. Here is at sigma 2. Here is at sigma 2. Right? So this is the thing that we're interested in calculating. Let's remember the Marshall conditions here. We have k1 squared is equal to 0, but k2 squared is equal to k3 squared is equal to 4. Because those guys are vacuums, these guys are master states. Okay, and then we also have firstly the C stuff that we insert right. Okay? So let's see. So how does this work? So now we're going to remember our formula for how to compute these correlation functions along with an insertion of the data x. If you remember, we had this nice rule which I just read off. And the rule was that you just calculate whatever you would have got with the e to the power I k dot x's and multiply by the factor for each insertion. You multiply by the factor minus I by 2 alpha prime times and in this case we've got only one insertion, so I'll just write it out for that one insertion. So sum over k2 mu plus k3 mu by z12 plus k3 mu by z13. Okay, we got this thing, the insertion at point z1, that was the z1 here, and then we're supposed to sum over all other k insertions. So 2 will k mu and so on. Okay, we should multiply by such a factor plus a factor of an alpha 1 mu and some oscillator that we have to contract, which you can think of as del x mu tilde, which you have to contract according to the usual big contraction rules. But now we've got only one of these oscillators, so the usual big contraction rules just give you 0. There's nothing for it to contract against. Okay? So that guy is just thrown away. This guy will throw away. And we take this and multiply it with what we would have got. Then we've got this, and then we've got times complex conjugate from the z part. So with the mu, this is with the mu, and then we have to multiply the whole thing with the mu. Okay? And then we multiply the whole thing by just the expectation values of this e to the power case. Okay? And that we know what that is. That's z12 to the power more. Okay, z12. So let me write just the analytic part. There's also the anti-analytic. Let's write the analytic. So z12 to the power k1 dot k2 by 2, z23 to the power k2 dot k3 by 2, and z13 to the power k1 dot 3 by 2. Okay, so now we have to simplify this. Let's first work out the formulas. K1 dot K2, we use the same formula as K1 plus K2, the whole thing squared, minus K1 squared, minus K2 squared, divided by 2. So that's K3 squared, minus K1 squared, minus K2 squared, divided by 2. But K1 squared is 0. And therefore and the K3 squared part cancels K2 squared part. So this term is just 0. So claim K1 dot K2 in this case is 0. Because it's K3 squared minus K2 squared, each of which is equal.
Can you have a full understanding of
this? This is just kinematics. You know, it's any field which has K1 squared equals 0. This thing, yes. So, right. Okay. Similarly, K1 dot K3 is equal to 0. However, what about K2 dot K3? K2 dot K3 is K1 squared, which is 0, minus K2 squared minus K3 squared, each of which are 4 by alpha prime, divided by 2. So K2 log K3 is equal to minus 4. Okay, I forgot to put the alpha prime. Yeah. So the net result from these factors, from the e to pi k dot x contractions, is a factor of 1 over z23 to the power 2. That's this. Is this clear? Okay. Now let's look at this term. What was this term? This term looks pretty complicated. Well, we can simplify it a little bit. We've got minus I by alpha prime by 2, and then we've got K2Z13 plus K3Z12 over Z12 Z13. Okay, but because we've got this power of K2 and K3 there explicitly, doesn't seem like it's simplified the numerators. It seems hard to imagine how that thing could be independent of Z. Nonetheless, it is. Can somebody tell me why? Very good. And transfers to what?
Okay, K's are always transfers. E mu are the polarizations.
Yes.
So it should always do that.
So what is transferred? So what is the equation?
So E mu nu K mu should be
Which K?
of K1.
Very good. E mu nu K1 mu is equal to 0. Okay? So now we can use momentum conservation of this. K3 is equal to minus of K2 plus K1, but the K1 part doesn't contribute because it contracts to 0 here. Okay? So basically a factor of K2 is the same as a factor of minus K. Okay? So we can write this in a more symmetrical fashion by replacing every time we have a K2, we replace it by K2 minus K3 by 2. As far as the contraction with E is concerned, it's the same thing, and every time we have a K3, we'll replace it by a factor of the opposite of that. So this can be written as minus I alpha prime by 2, let's say by 4, and then we get K23 mu. K23 is K minus K3 into Z13 minus Z12 over Z12 Z13. Okay, so now this is equal to Z23 over Z12 Z13. Okay, and now we combine with this. So the net factor is 1 over Z23, Z12, Z13. Okay? Now this cancels what we get from the C's. We have something similar from the complex conjugate part. And so, in the end, what do we have? In the end, we have alpha prime by 16 in our position. Alpha prime by 16, K23 mu, K23 mu, E mu. very useful because numbers have one alpha, right? Two. We'll be doing a consistency check on this, but we'll come back to the number behind this in a little bit. Right? Oh, because we have a square. Yeah? Well, just seems to lack square. Unless I messed up with something else. Okay, we'll come back to that number. Alpha prime. The alpha prime came from this rule, which we had this rule. We had one of these factors for each of the left and the right. I don't see how you can not get an alpha prime square. But let's get back to this when we have a check. We'll have a check. Okay. Certainly this is a form, and anyway this is up to undetermined this. So there's gt squared g massless times cs. Okay. And now as a final exercise, what we'll do is calculate the three massless vertex operators. Was the same factor we have whenever we do a calculation on the sphere. And some determinant which we're not keeping track of. Okay? So finally now we're going to do the calculation of three massless states. So it's a little more messy, but let's just at least understand the structure. Okay, firstly we're going to have an e to the pi k1 dot x e to the pi k2 dot x e to the pi k3 dot x. But now each of these k1, k2, k3 is squares to 0. So the path that you get just from the contraction of the exponentials is 1. Right? Because you have k1 dot k2 is equal to k1 plus k2 the whole thing squared minus k2 squared minus k3 squared, which is equal to 0 minus 0 minus 0. So you get nothing from the contraction of the exponentials. Okay? So that part we can clear off. So all that remains is the part that we get from oscillator contractions. Okay? So now from the oscillator contractions, what do we have? We have this I by 2 alpha prime, and then k2 over z12 plus k2 mu over z12 plus k3 mu over z13. But now this is going to be contracted with a polarization vector of 1. Okay, so as we saw before, in the process of this contraction, we can replace this by k2 minus k3 by 2, and so we get a factor of 4, and replace this by k23 mu divided by z12, z13, and then z23. Okay? Plus we have del alpha tilde at sigma. So we have a product of 3 such factors and then complex conjugates. Okay? So the other factor is I by 4 alpha prime, and now cyclic. Right? So this will be k31 mu z31 over z23 z21 plus del x tilde mu at sigma 2. Okay? And I by 4 alpha prime k12 mu z12 1, 2, Z 3, 1, Z 3, 2, plus del alpha tilde mu alpha sigma. Okay, and we're supposed to take all weak contractions of this. But what can we do? We can't weak contractions of odd numbers of oscillators. No? So what we can do is weak contract things pairwise. So you see that we get 4 terms. The first term is when we just take the product of these things. Okay? And the second term, the next 3 terms are when you take the product of one of these and weak contract it with any 2 of these oscillators. Is this clear? Okay? So, let's just check the Z1 to the Z dependencies in each of these. If we take the product of each of these, you see clearly that what we're getting is 1 over Z12, 1 over Z23, 1 over Z31 in the denominator. We have a product of that, a factor of that thing squared in the denominator and a factor of it in the numerator. On the other hand, suppose we take the product of this guy with the contraction of these two. This will give us a factor of Z23 squared. 1 over Z23 squared. Because the log is twice differentiated. The log, which is the weak contraction of the x's, is twice differentiated. Okay? That multiplied by the Z dependencies here, once again give us 1 over Z12, 1 over Z23, 1 over Z13. Right? There was a Z23 in the numerator here, it becomes Z23 in the denominator because you have a 1 over Z23 squared. So all of the terms have the same Z dependence, exactly the Z dependence that will cancel with the Z dependence from the C side. So the Z dependence we use from, okay? And then we just have to keep track of what we get when we contract in index space. In index space, contracting this guy and this guy, so this was mu1, this was mu2, this was mu3. Gives us a delta value. Okay? So, this index structure of what we're going to get is K1 mu1 times delta of mu2 with mu3 plus K2 mu2 times delta of mu1 with mu3 and so on. Okay? So now that you've seen the structure, I'm just going to write down the answer. Is this okay? We're going to get a sum of 4 terms, both from the left and from the right. And so let's write it down the way he writes to. He writes it down as E1 mu E2 alpha beta E3 gamma delta, then contracted with T mu alpha gamma T nu beta delta, where each of these factors is the factor you get from the left and from the right. Okay, each of these factors is the sum of 4 terms, and the sum of the 4 terms are K23 mu eta alpha gamma plus K31 alpha eta nu mu plus K21 gamma eta mu alpha plus alpha prime by 8 K23 mu K31 alpha K12 okay. You see where each of these terms comes from, right? This term is this guy with this contraction. This term is this guy with these two contracted. This term is this guy with these two contracted. And this term is the product of these three. got some index structure on the left, index structure on the right, contracting with the first index and the second index of the polarization. Okay, and all of this now is going to be multiplied by the CS2 times G masters the whole thing cube times. That's it. Okay, now you see we've already started computing interesting things. The fact that that 3 tachyon amplitude was independent of K, okay, was more or less this, was the statement that the 3 tachyon vertex can be represented in a Feynman diagram with just a phi cube term. The fact that the single graviton with 2 tachyons has some K dependence will, as we will see, come out of the fact that this term is an interaction in a low energy effective action that involves the coupling of graviton to the tachyon field, and this interaction will come out of you see this interaction is the stress tensor from the tachyon interacting with the graviton. That's the T squared term, the stress tensor of the tachyon, which interacts with the graviton, and that's what's going to reproduce this interaction. Whereas this 3 graviton interaction is simply the 3 graviton interaction from the Einstein diagram. You know, if you just take the Einstein action, expand it as eta plus h, okay, and compute the cubic terms in that process using physical state conditions, meaning transfer sanity of the gravitons. You just did a Born calculation, a classical calculation of 3 graviton waves coming in interacting with each other. This is the structure that we get. We'll probably see this in more detail once we start talking about the effective, when we start talking about the master's effective action stream. Okay? But we've got a little more information here than just from the gravitons, because we've done all the master's states of string theory together. We've done the dilaton, the mu field, and the graviton. So this computation here has already a lot of information. It's telling you how the master states of string theory interact with each other, and I'm claiming that at least partly, we will have a lecture seeing this in more detail and how this thing reduces to a known effective action. There's a lot of information in this calculation, and this information that we will soon summarize in terms of an effective action. Okay? So, although 3-point functions are relatively boring, already these 3-point functions, just in their polarization information and the dependence on momenta and so on, already these 3-point functions start giving us interesting information about what these master states of string theory are and how they interact. Exactly how we interpret this in terms of low energy effective as Lagrangian, hang on, we come. Okay? Fine. So these are the 3-point function calculations I want to do with you guys in class. Any questions or comments about it before we move on to 4?
Why not two masters?
Why not 2 gravitons and a tachyon? Now, good. I think that probably should vanish. You see, the tachyon potential in string theory starts at T squared. Right. Okay. Firstly, honestly, I didn't try to calculate this, but okay, it's my strong suspicion that this should vanish. Basically, you see, because what the effective action of the tachyon is quadratic coupled to gravity. So let me say this again: had 2 gravitons times tachyon not vanished, then the gravity background would have sourced the tachyon. It would have been inconsistent to look at a pure gravity solution, string theory, which is not the case. Yeah. So I think I haven't done it. I haven't done it in this round. I'm sure I've done it at some point. But it's a good exercise. Calculated. I think you should find it. Okay. Other questions on this? Okay, very good. So now the next thing we're going to try to do is to stay to the sphere, but turn from 3-point function calculations to 4-point function calculations. Okay? And in doing this, we will encounter one of the classic formulas of string theory, the formula that gave birth to string theory, and is a closed-string version of Venezian amplitude. Okay. The Venezian amplitude. It's called Virasoro-Shapiro amplitude, right? Version. It's the formula that was discovered before string theory was, and whose study, in some sense, led to the birth of string theory. Okay. So what we are going to try to do is compute the scattering amplitude of 4, just say to start with, just 4 tangents. Okay? So what do we have? We've got e to the pi k1 dot x, e to the pi k2 dot x, e to the pi k3 dot x, e to the pi k4 dot x. Okay. And now to keep life simple, what I will do is assume this formal result that we've seen, that things don't matter, don't depend on where you keep the fixed vertex operators. So as to fix 3 of the vertex operators at specific points. And through trial and error, you soon see that the 3 specific points that make life simplest. No, it doesn't matter. Actually, at this level, you can just keep them all arbitrary. It's easy as cancelling. But there is a standard to choose one of them to be 0. The other to be 1, and the third to be infinity. Now this infinity we will choose to be some m which we will take to infinity. So we have to write infinity. Okay. And this fourth graph we just take to be z. So these are the 3 fixed vertex operators. Okay? Those are the 3 fixed vertex operators. And this is the chapters of base. Okay, so what do we have? Okay, so let's compute. Firstly, I'm going to be taking m to infinity. So the first thing I want to see is that all dependence and that this doesn't give me either 0 or infinity. Okay, this is a little bit part of the test that things don't depend on where you insert things. So let me compute all the dependence on the location of the third domain. So from the C's, what do I get? From the C's, I get Z23 to the power k2 dot k3, which, since we're taking Z3 to infinity, will be like m to the power by 2, k2 dot k3 by 2. And I get a Z31. This is the dependence on m from the correlation function of the C's. Okay? From C's. Okay. Now let's look at the dependence on m from the correlation from the contractions. From the contractions, what do we get? Okay, first let's simplify this. This is well, okay, let's just.
So all are calculus, right? This should be.
Yeah, you saw
Minus 1 by the.
No, you see now the momentum conservation. No, you're completely. So you're completely right. So this is just m to the power. So there's alpha prime here. There's alpha prime here. And so each of these is, as you said, minus 2 by alpha, right? As we've seen before. So we get m to the power minus 2. No, I'm sorry. That's wrong. Let me say it wrong. You see, no, it's not right. You see, because we use the fact that when we have 3 tachyons, the sum of 2 tachyons, sum of momenta of 2 of the participants was a momentum of the third one. That's not true anymore. You see, what we have is momentum conservation tells us that K1 plus K2 plus K3 plus K4 is equal to 0. Okay, so if you get K2 plus K3 the whole thing squared, that is not necessarily formula. You see, so K2 dot K3 is equal to K2 plus K3 the whole thing squared minus K2 squared minus K3 squared by 2. That's true. But K2 plus K3 squared is nothing simple. Is it clear? Okay, so let us continue. Okay. Now let's look at what we get from K3 interacting with all these other guys. Okay.
There's another problem.
What is the other problem?
Maybe K3, K4.
There's no C contraction between K3 and K4 because K4 is not a fixed vertex point. It says C is a this is not working out. Okay, I messed something up. Let me just go through it completely. Then I'm going to check it. Okay. Okay. So now let's look at the dependence on M that comes from this guy from the e to the power, the contraction of the x's. So what do we get? We get m to the power alpha prime by 2. Sorry. I'm mixing up things. Let me start this again. Here, okay, let me start this. Sorry. Okay. So from this, let's do the C's. So the C's are just a factor of M from this guy and M from this guy. Because from the C's we get Z32 times Z3. Okay? So from the C's we get M squared. Because Z32 and Z31 are each M becomes very large. Okay? Right. Sorry. This is what we got from the C's. Then what we get from the X's involves the K's. But that involves all operators.
Yes, so there are 6 Z's.
Right. There are 6. We're only keeping track of at the moment of the contraction M and something else. Okay? So that gives us M to the power alpha prime by 2 into K3 dot K1 plus K2 plus K3. Okay?
That's minus 8.
What?
That's minus 8.
That's minus 8. That's right. So this is equal to minus K3. Okay. And now we can use the Marshall condition. Okay? Now we can use the Marshall condition. So K3 squared is equal to 4 by alpha, right? So this is equal to M to the power minus 2. Okay, so all N dependence has vanished. Okay, so what remains? Let's see. From the C contractions, we get a Z2 minus Z1, the whole thing. A Z2 minus Z1. But Z2 is 1, Z1 is 0, so Z2 minus Z1 is 1. Okay, so we have nothing else from the C contractions. Okay, what about from the X contractions? We have one contraction between this and this. So that's also 1 to some power, so we don't care what the power is. Okay? All that remains is the contraction between this and the contraction between this and this. that's what goes out. So the contraction between this and this is e to the power is now this is z minus 0, so it's just, so let's say that the location of this is z. So this is z to the power k1 dot k2 alpha prime by k4 alpha prime by 2. And here we get z minus 1 only the whole number. I'll multiply it. I'll mod square it. Okay? And z to the power alpha prime by 2 k3 dot k4 z minus 1. Where? Here? This one?
Yeah. 2 is
2. Right. 2. Okay. Then when we multiply with the anti-holomorphic, we just mod square this stuff. And we have to integrate. So our final answer is d2z d2z mod z, the whole thing. Let's write it. Mod z alpha prime k1 dot k4 and then what z mod k2 with an alpha prime. Okay.
So maybe like k1 plus k2 is k3 plus k4 and then
Good. So let me do this rewriting in more invariant ways. Exactly as you suggested. Okay. So now let's pause from this formula to just examine the kinematics of this situation. Okay. So what are the invariants in 4 particle set? So one can write down. Well, basically there are 2 invariants. But in order to write things a little symmetrically, we'll define the formula. Let's define k1 plus k2, whole thing squared is equal to s. k1 plus k3, the whole thing squared is equal to t. And k1 plus k4, the whole thing squared is equal to t. Okay? Of the other, so we've taken 2 combinations of 2 momenta. We could have taken combinations of 2 other things. But any other combination like k2 plus k3 would by momentum conservation directly be the same as k1 plus k4. So we don't need to take any other combination. There's 3 ways of dividing 4 objects into groups of 2. Not choosing questions. Fine. So you might think that, oh, okay, these then will be independent. But they're not, because of the mass check condition. Okay? So let's check. Let's add the 3 of these together. Okay, so if we add the 3 of these together, what do we get? We get k1 squared 3 times plus k2 squared plus k3 squared plus k4 squared and then plus 2k1 into k2 plus k3 plus k4, but that's minus k1. Okay? Which is equal to k1 squared plus k2 squared plus k3 squared plus k4 squared, which is equal to 16 by alpha prime. Okay? Now, I think Kolchinsky puts an alpha prime in the definition of S. Check that. No, he. So when Kolchinsky writes this identity is alpha prime into an S plus T plus U is equal to 6. given this identity, there are only two invariants in the scattering, and these two invariants are easy to understand. You made it two particle scattering. So the invariants are essentially the center of mass energy and the angle at which the scattering angles. Is the energy at which you scatter and the angle at which things come out. Okay? Right. So that's that. Now we want to rewrite our formula in terms of these invariants. So let's quickly do that. Let's see if we can do that nicely. So that's very simple because K1.K4 is equal to K1 plus K4 the whole thing squared minus K1 squared times K4 squared by 2. And we're interested in alpha prime times this is alpha prime. This. But that is equal to alpha prime times U by 2. And now this is 4 by alpha prime. So minus 4. Okay? So similarly, we can write this guy K2.K4 as T, right? So this thing is G2Z, okay, Z to the power alpha prime U by 2 minus 4, 1 minus Z to the power alpha prime T by 2 minus 4. Now this formula looks like it picks up T and U as special, and discriminating against Z, for instance. But actually, that's not true. You can change variables in this formula from Z to 1 by Z. Okay, and in the new variable you get the same formula, but with U and T replaced by the guy that's special for the chap at infinity, which was K3. So it will be. So let's see what was special here. The guy that was special here was guy at 1, and we got 1, 3, and 1, 4. So we get there 3. Then we get 3, 4. Sorry, what do we get? So, sorry. So the guy that was fixed to infinity, was K3, and so we will get.
This S is also equals to K3 plus K4 squared, right?
Yeah. S and T maybe, that's right. Yeah. Sorry, you get, I'm not 100% sure. You get two others.
S and U, because U will have K3. K3 was the one with M. So here if you look at these two formulas, you don't have 3 in S and U. But you can rewrite them as K3 plus, if you apply the momentum conservation.
Yeah, that's probably right. Actually, I'll you get the answer. So basically, this formula is completely symmetric. Is completely symmetric in S, T, and U as it should be, because these things are interchangeable under the relabeling of the point. Okay, now the key point that I want to make here. Well, okay, so we're going to have to stop there soon, actually. But let me make 2-3 points. Okay, The first point I want to make is the following. The first point I want to make is that you might, when you look at this formula, wonder about whether this defines a convergent integral. Okay? You see, suppose this power was smaller than 2 and this power was smaller than 2. Sorry, so suppose this power was smaller than 2, then this integral, the integral will diverge at 0. If this power was smaller than 2, then the integral would diverge at 1. And if the sum of these two powers was larger than -2, then the integral would diverge at infinity. Right? Because the infinity will go like z to the power sum of the powers, and that had better go die off faster than 1 by z squared in order to get a convergence. Okay, so the first, now certainly for some values of u and t, and for x actually, of course, this integral does diverge. But the first question that you might have in your mind is, are there any values of x, t and u for which it's a convergent? And the answer is yes. You see, suppose this was equal to 2, this was equal to -2, so that this was, the integral here was at the edge of diverging, and this was equal to -2, so the integral here was at the edge of diverging. Then at infinity we've got -4, which is a safe cushion away from -2. Okay, so we could make this -2.5, -2.5, we can make this, we can make this -1 and -1, which are both safe. Well, -1.5 and -1.5, which are both safely convergent at these 2 points, and will still be -3 at infinity. Okay, so there is a range in the space of S of u and t in which this integral is a convergent. If we go outside this range, the integral diverges. Okay. However, as we will see, though we will have to see this next time, as we will see, we will be interested in this function as an analytic function on the whole STU, or on the whole STU, as an analytic function of complex u and t, for instance. Okay? The way we're going to make sense of this formula is by evaluating it where it makes sense. Where it's given by convergent integral. That will give us an analytic function of u and t. We will find that where it starts to stop making sense, that's because this analytic function has some singularities. But the singularities will all turn out to be poles. Because they're poles, we can analytically continue on. Okay? So basically, we're going to, by analytic continuation, by using the fact that it's well defined in some region, we're going to evaluate it in that region, and then by analytic continuation, find the answer. When we adopt this procedure, we will get an answer beyond the range of convergence of this integral. But the answer will have several singularities, which will turn out to be poles. And these poles will be extremely physical. The poles will represent the singularities due to exchange of intermediate particles. So our next job is to take this, but firstly to evaluate this exactly. It's possible to evaluate this integral exactly in terms of gamma functions. Okay? But most presently to study the pole structure of the final answer, the singularity structure of the final answer. Okay?